Hello everyone. In the previous lecture we had derived this expression or we had rewritten this expression in terms of this variable w along with this bending rigidity. What we are going to do next is to substitute this expression back where we had left off earlier in our derivation steps, right here. Right, so what I'm going to do is just copy this entire thing, which is the negative of the left hand side that we have been dealing with. So this thing, copy it in a new page. This is our minus LHS bending, and this entire thing that I'm going to replace by minus d delta port w. All right, let me do that immediately. Minus d delta 4w. I'll just move this here. Okay, next what I'm going to do is to put this minus sign from the left hand side back here. So this is minus, this becomes a minus, this becomes a plus, this becomes a plus, and this becomes a plus. So there we have our left hand side considering only the bending terms. Next we are interested in finding out the right hand side, and please note that this right hand side is the right hand side of our virtual work equation. Okay, so back when we started our derivations, we had started from this side and we had just started off with this left hand side. Now we are going to consider this right hand side here. Okay, so we are going to consider this di delta ui dA. Now what is the, so this is the externally applied load. What is this load? Okay, so let me go back to the first equation, to the first page that we were considering. So this diagram, and here I need to show the load, the externally applied load, in this particular fashion. So let there be some kind of a distributed load present over this top surface, that is at z equal to minus h by 2. But please note that because of this downward direction of z, this is in the positive direction. Okay, so let me get back to my page. So this thing can be written as q delta w dA. So all that I have to do is really to equate this thing with this thing, and please note that the right hand side that I have written, that really is just considering the bending term, because this kind of a load is what is going to induce the bending. Okay, so you might as well write this as the bending term. All right, now if we equate these two things, then we are going to end up with I wish to write these two things together. What I can do is just by the way, it is a little bit more explicit and clearer if all these terms involving the boundaries So these integration terms uh, over the entire contour of our plate, that is expressed uh, in terms of this cyclic integral. So that's what I'll do, and you will see that in the typeset lecture notes, these are also presented in such kinds of, or denoted by such kinds of cyclic integrals. I don't have to put the cyclic integral over this thing. Okay, so I'll make it all consistent all throughout. So wherever I have those integrations over the contour, uh, I'll use the cyclic integrals. It doesn't make any difference to our maths, but it's just more explicit this way. All right, and it will be also consistent with the notation that we use in our typeset notes. So if I just copy this thing and paste it here, I am in a little bit of a trouble here because this entire thing won't fit here. Okay, I'll go to the next page. Right, this should do it. So but basically I'm just doing this. All right, now of course I can bring this to this left hand side. I'll do that. All right, now uh, here you please note that a little bit of uh, little bit of simplification is still possible uh, if we consider the stress equilibrium equation. So that's exactly what you are going to do. Consider the stress equilibrium equation uh, along the x direction first. So what is the stress equilibrium equation in the x direction? It is simply this del sigma xx del x plus del sigma xy del y plus del sigma xz del z. And please note that we have already considered, we are already considering a situation where the boundary terms or the body force terms are being neglected, so we don't have to write that plus rho bx. So what I'm going to do here is to will multiply all these terms by z. Okay, and then I'm going to integrate it with respect to z. Okay, so integrate with respect to z from minus h by 2 to h by 2. So what I'm going to obtain uh, here is, let me just write that down, and you'll see in a moment the motivation for doing such a thing. Right now it may seem a little bit, I mean, none of the steps is wrong, but why are we even doing this? It may seem like that, but you will soon realize the motivation. I mean, the ultimate goal here is to come back here and to simplify some of these expressions. Okay. So So next, what we are going to do here is you see, this z is well, it is independent of x. So what we can do is we can put this z inside here. Similarly, this z is certainly independent of y, so we can put this z inside here. And so we'll do that, and I'll show you a certain simplification that is possible, but we can't do such a thing here for this term. All right, so what we are going to do for this one is to carry out an integration by parts. Okay, so let me go to the next page and continue with the steps. Like so. For the second term, I have this. Sorry, it should be sigma xy. And then for the term involving the integration with respect, or the z sigma zxz term, I'll have, after the integration by parts, these boundary terms and this integration term. Right. Next, you note that this del x, it can very well be taken outside this integration, right? So if you are a little bit observant mathematically, you can actually see that there is a certain danger to writing or doing such a thing, that taking a differentiation out of this integration. What I'm trying to say here is that you need to respect something called the Leibniz rule, but for this particular case, there is no danger because the upper limits and the lower limits, uh, they are constants. Okay, so if you are not familiar with the Leibniz rule, I seriously advise you to please look it up. Okay, which actually puts uh, that rule is regarding this taking the differentiation that is present outside an integration within the integration. So in this particular case, it doesn't really matter, but it will matter. It would have mattered had these things not been constants, rather uh, some functions. Okay, so for now we just proceed. Similarly, we take this thing out of the integration. Now this particular term, uh, this sigma xz on h by 2 and sigma xz on minus h by 2, they are actually 0. Okay, so you can look from the diagram that the only loading that is present, that is along the z direction. There is no shear there. Okay, so the sigma xz, it represents the shear stress. We don't have any shear stress on the top surface and on the bottom surface, so these terms are 0. These boundary terms are 0. We are left with just this. Next, you note that this particular combination, we have already defined this to be mx. Okay, so this is nothing but mx. This is nothing but my, as we have been writing it earlier. And this particular term we have not defined, but we can do so. So let me write this down. This is del mx del x plus del my del y. Uh, Sorry, this is actually, sorry, my mistake. This is mxy, because I have sigma xy here, not sigma yy. Had this been sigma yy, then this would have been my. Uh, Now, this particular term that I'm going to define as qx. I'll take this thing out to the right hand side. So what we're doing here is to define qx as sigma xz. Uh, by the way, I have made a mistake here in the integration by parts, because you see, uh, when I carry out the integration by parts, in the second term involving the integration, there is a ddz of z. Okay, there is a ddz of z that should be done. So in the next step, this thing is going to disappear. Okay, so this is just sigma xz dz. All right. So what is this? What this is telling us is that over a particular uh, edge of our plate. So if our plate is going like that, is okay. So this is the thickness of the plate, and on this edge we have, so if you're taking a cut section through the plate, over the thickness, over that edge, you are going to end up with stresses which are like this sigma. So these are our sigma xz. You please note that when I'm doing such a thing, I am considering that the x is coming out like this. Okay, so if we go back to our first diagram here, so what I'm doing here is taking a cut section which is perpendicular to the x-axis. So over such a kind of a cut section, over the exposed edge of such a cut section, uh, let me try to draw that here. If I take a cut section in this fashion, all right, and this is just for demonstration purpose. So this angle is 90-degree here. If I take such a cut section, then the exposed surface as a result of that cut section, I'm considering that thickness, that edge. Okay, so I'll delete this thing to avoid the clutter and get back to my page. So I was working here. All right. So here I have the sigma xz, and it is that sigma xz which is actually contributing to the ultimate shear force, which is represented by this ux. Okay. Now, in exactly the same fashion that we have obtained this equation, next if we consider the stress equilibrium equation in y direction. So earlier, as you can see, we have taken it along the x direction, and now we are going to take it along the y direction. So what we're going to have is del sigma xy del x plus del sigma yy del y plus del sigma yz del z, that is equal to 0. And if we carry out the exact same kind of steps that we have just done for the stress equilibrium equation along the x direction, that is multiplying throughout by z, then integrating, then what we are going to obtain is del mxy del x plus del my del y. This my I'll be getting from this term, and this mxy I'll be getting from this term. And from here, what I'll obtain is a qy, where you please note that we are defining qy to be minus h by 2 to h by 2 sigma yz dz. And you can interpret this shear force by taking similarly a cut section which is perpendicular to the y-axis in just the same way that we have done here. Okay, so so if we get back to our steps, what does this really tell us? Okay, uh, if we just take a look there, here you see I do have a term involving the del mx del x. I do have a term involving the del mxy del x. Del mxy del y. And the good thing here is that I have missed a delta w, but you please note that barring that error, I'll correct that immediately. This nx, and we also have an nx here. We have nx here, we have nx here. So it is very much possible to take this term common with this term. Similarly, it is possible to take this term, which has a ny here, common with this term, this delta del my del y with this ny. Okay, so let me copy this entire thing again. Okay, first of all, I will take this term common with this term. So whatever was present in the first line, that will remain as it is. So I'll just copy paste from there. But here, what I will have is this delta mx del mx del x plus del mxy del y nx delta w ds, cyclic integral over the entire contour. And next I'll take this term common with this term, so that I obtain del mxy del x from here plus del my del y multiplied by ny, which is present over here as well as here, and then the delta w ds, and then I'll have this term. Integration over the entire area, d delta 4w minus q delta w dA. So I can replace this thing, but by what I had obtained in the previous page, this was qx and this was qy. So you can just check this entire thing is qx and this entire thing is qy. So back here I'll be able to make that substitution. So I'll copy this entire thing here, go to the next page and write down that equation. So this entire thing becomes qx I shift this here, and then this is qy and I shift this here. I'll just shift this thing here. All right, so this entire thing is equal to 0. Okay, right. Now this is as far as we can go here without I mean in terms of the simplifications that are possible. Now the next step, and uh, this is where it gets uh, uh, quite involved as far as the geometry is concerned. We are going to convert these equations written with respect to the xy coordinate system uh, or with respect to a coordinate system now, which will be like a body fitted coordinate system. So what we are saying is that if I just go back to this diagram and maybe copy this thing out. We have been referring to this xy coordinate system, but what I want to do now is to go to an equivalent picture. So if I look at it from the top down, I'm going to look at it and I'm going to find the shape to be of this fashion, something close to this, not the perfect of transpositions, but bear with me here. So our x is like this, our y is like this, and z is going into the plane of the screen, represented by this cross. Now what I really want to do here uh, is to consider a coordinate system which will be body fitted like this. Okay, so I'll consider a coordinate system which is s like this and n like this. So s is along the contour and n is everywhere perpendicular to the contour, and it makes sense to treat it in this fashion because you note that in the process of these previous steps we have basically integrated in all these terms we have integrated through the thickness with respect to z from minus h by 2 to h by 2. So you see none of these terms explicitly contain any integration with respect to z. That has already been taken care of or somehow been absorbed within the terms. So all that is left is a consideration over this domain. So it is as if we are only concentrating on the flat mid surface or on the mid surface of this plate. So and you see overall this term here is over the entire domain, but all of these terms, okay, these terms are over the entire boundary. So that is kind of the motivation here, is that we wish to go to a coordinate system which would be distributed over this, or which would be tracking this entire contour here. Okay, one good thing here is that even if we convert our entire equations to another coordinate system like this Sn, it would not make any difference to this term here, because you see this has been written in this tensor notation, this delta 4 or this operator notation, and that particular form that won't be affected by a different choice of the coordinate system. Okay, so that's good news, and our hope is that if we go from the xy coordinate system to the Sn coordinate system, then perhaps these terms will also uh, be somewhat simplified. But the price that we'll have to pay for eventually arriving at such a simplified form will be some due labor in the process of doing it. So on that note, I will end this video, and in the next one we'll continue with that transformation from the xy coordinate system to the Sn coordinate system. Thank you very much.